Fernando. Welcome everyone to this 25th webinar of the ISGAN Academy series. And in today's webinar, the speakers will explain you how to extract value from data sharing from renewable energy sources forecasting, looking at privacy aspects and data monetization. As they will present later, but Ricardo Vesa from Inestec and Lian from DTU will make the presentation on this topic. Just I will briefly introduce the ISGAN and the work we do. So next slide. So ISGAN is a strategic platform to support high-level government knowledge transfer and action to accelerate the development and deployment of smarter, cleaner electricity grids around the world. This is a joint initiative from the International Energy Agency and the Clean Energy Ministerial. And this is the only international global government-to-government forum for smart grids. We are divided in working groups called annexes, so all of them are, except for Annex 1 that is finished and was to set up ISGAN. The rest of the annex are active. So Annex 2 focusing on the smart grid case studies, Annex 3 cost-benefit analysis and toolkits, Annex 4 synthesis insight for decision makers, Annex 5 on the International Research Facility Network, Annex 6 on transmission and distribution power systems, Annex 7 looks at more smart grid transitions, and Annex 8, the ISGAN Academy, we focus on learning through this online platform, and this webinar is one of our main activities. So next slide. We are currently in 26 countries, as you can see in this map, and in addition to the European Commission. And finally, on the work we do, next slide. We organize different conference, presentation, policy brief, technological brief, technical papers, webinars, casebook, discussion papers, workshops. All this information is public available in our website. I encourage you to visit them. And the link also to all these webinars are as part of Annex 8. I just want to also make a strong point here that we have a strong international network expert that contributes to make ISGAN possible. We have a global, regional, and national policy support as well, knowledge sharing, technical assistance, and project coordination. And we have key strategic partnerships with the International Energy Agency, Clean Energy Ministerial, the Global Smart Grid Forum, Mission Innovation, and other international initiatives and organizations. So with that said, I welcome the speakers and thank you for your interest and hope you enjoyed the webinar. Thank you. Ricardo.
Okay, thank you, José Pablo. So my name is Ricardo Bessa. I will be the first one to present. So I will briefly present the Smart for Res project. You can find a previous webinar with more details, a previous ISGAN webinar with more details about the project. So I will very quickly present it. Then some motivation for data sharing and use cases on collaborative analytics. Then an example that a use case we are constructing in Smart for Res for collaborative forecasting of renewable energy. And then my colleague Lian will present the data markets concept and the Smart for Res proposal. So going now to Smart for Res, so this is an European project. Our vision is to cover the full value chain of renewable energy forecasting. So starting from weather modeling and forecasting, going them to power and new business models like data markets, and also handling the decision aid models for different use cases that use uncertainty forecasts from renewable energy as an input. So we are going from the accuracy that we want to improve to the value of forecast that we also want to improve the decisions that are made with this information. So this is an holistic approach. The presentation of today, it is focused on this point here. So improvement from collaborative renewable energy forecasting. And it is known from the literature that we can have 20% improvements for 6 hours ahead solar energy forecasting and between 15 to 20 for wind energy. So this is something we know for true. It's validated in real data, in real problems. What the gap we want to address on this project is the lack of privacy guarantees and price-based incentives to share data. So sharing data has benefits, but privacy is a barrier. And also you probably also need to have some kind of financial incentives to share this data. So the Smart Forecast Consortium, we have 6 countries represented, 12 partners. We cover the full value chain. So we have end users, industry, research and university, and also methodologies that we know that this is an important input for renewable energy forecasting. Project started 1 year ago, and it will last until 2023. So as I said, if you want to know more details, you can visit our website or see the previous webinar on ISGAN. So now going to the main topic of this presentation, the motivation to data sharing and collaborative analytics. So one motivation is that we are starting to have an increasing volume of geographically distributed data. This can come from PV panels, wind turbines, smart meters, electric vehicles, weather stations, and also with the advent of Internet of Things, we are starting to have different devices and sensors producing a lot of data. So we have all these data from different locations, and that's one reason also trying to extract some value from it. We know that you can improve forecasting accuracy by using this data, but we also know there is 3 main barriers for this. One is data privacy and confidentiality. So some of this data is personal data, other data is business sensitive data. So there is always an issue in sharing this data. There is also a lack of economic signal. So you probably would be willing to share your data if someone pays for it. So that's also a barrier. We have to define how should you price data, and then the lack of business cases for collaborative analytics. So what is collaborative analytics? So what you have here, it's a typical setup on a machine learning problem. So imagine that you have your own machine learning problem that you want to solve, and you are using data from 3 different owners. So green, purple, and gray are different data owners. And so you are constructing the data, your model, by combining data from these three different owners. If they have privacy issues, they will not share the data, so you don't have all the data you have here. The current state of the art is federated learning. So you probably hear these on some projects from Google, from Apple, from IBM. They are looking and working a lot on federated learning. Federated learning means that you don't combine the data. It means that you build a local model with local data in a worker. So what you get from the data is just this model. So the weights, for example, of a neural network, and you do this for each data owner individually without combining their data. And what you combine in the end is in fact the weights you get, or the local model that you get from each data owner, and you aggregate them, and you have one master node or a master model that have the information from these different data owners. So this is state of the art, is what is being nowadays a hot topic. What Smart Forecast, these are the principles of data sharing in Smart Forecast. And our principles is that we don't exchange raw data, so that's a no. We don't exchange model coefficients like you see here on federated learning. You will see where is the difference. So we partially don't do that, and we want to exchange model outputs. That's the concept of data markets, for example. And another important difference is that our data is divided by features and not by observations. What you see here is that data is divided by observations. And in renewable energy forecasting and in different problems in the energy sector, you don't have data divided by observations, you have them divided by features. So I will tell you some use cases or potential use cases for data sharing. This use case is exactly what we are doing in Smart for Res, and I will present in the next slides. So we want to combine data from distributed PV panels or distributed wind turbines in one model, a prediction model. And we have two barriers, as I said: privacy, because they might be competitors in the same market, and also monetization, because you have to create some kind of incentives to share data. And you can also have other data like satellite images or sky cameras. And here the challenge is monetization. So how much should I pay, or how much should I price sky camera data or satellite image data? And the benefits, as I told you, is improvement on forecasting accuracy. And another use case is the liberalization of weather data. You see here on this map all the weather stations in the world, and you see here a lot of value in using this data. And so the key question is, how should I price my weather data? So this use case is somehow you starting to have access to a large scale network of weather data, but they need to make some kind of business out of it, so they could start selling their own data to different buyers. So that's another use case for weather modeling. On peer-to-peer trading, we know that this is also an hot topic. A key goal is, in fact, to have access to the transactions and the energy usage data. So some buy and sell electricity. If you have access to this kind of data, you can build more models on the top of it. You can do secure analytics with personal data to support better decision-making and trust from the consumers. So privacy of transaction data on the peer-to-peer market, it's also another potential use case. And finally, the last use case, power transformer conditions. So you want to know if your power transformer, what is the condition, if it is good, fair, or poor. Well, the poor is the one we actually want to predict. So one possibility is that you have utility C using data from other two utilities and a model that was constructed with this data. Why? Because this utility might have data, but it doesn't have faults or data from sensors for their own transformers. So it's willing to buy data from other utilities that also have power transformer and use that data to build the knowledge for example, to forecast the condition of a power transformer. And with that, it can improve maintenance policy. So those are some of the use cases we thought. So as I told you on Smart for Res, the main use case we are covering now, of course, we want to explore more. It's a collaborative learning for renewable energy forecasting. So collaborative learning means that you have different PV power plants or different wind power plants. You have their time series, so the measured values, and we combine all the measured values in a vector autoregressive model that is a linear model. That, as you can see here, what we do is that we forecast power for this example is just for two PV sites. So we forecast power for the two PV sites as a function of the lagged power observations of the two PV sites. So this means that if someone have access to the data that is used to construct this model, they will know the private values of the two PV sites. So if model one, wind farm one or PV farm one is using this model, would know the production of two. So there is some confidentiality breaches here, and this is what we are trying to solve. So in the end, what you want to get is to estimate your constant terms and the coefficient matrix by using data that it's a combination of multiple time series. So the state of the art, you find a lot of publications that work on this. It's to apply alternating direction method of multipliers for distributed learning. What this means, it means that you break your data, so your power data and your explanatory variables, by the data owners. So this means that this one only have access to this data, this one only to this data, and this one to this data. So it seems that the problem is solved. So if it is like this, so no one shares data and the problem is solved. It is not solved because this is an iterative method. So you have to have some kind of a conciliation matrix. And inside that matrix, you have all your private information here. So as you can see, so if someone it's have a good knowledge of mathematics, they can manipulate the information and get your private data. So the big limitation is that with some knowledge, you can actually get your data. So it's not, you don't have guarantees of privacy. And that is the big limitation. So what we are trying to do, so we are using the same model. So power for multiple locations, what we want to predict, lagged power observations for those locations, and we want to estimate the coefficients. What we do an encryption. So we have an encrypted version of the power, encrypted version of the explanatory variables, and encrypted version of the coefficients. And to get first the encrypted version of the power, we just generate randomly 3 matrices that are they are unknown to all agents, but they are built for, this one was built by agent 1, is the only one who knows this matrix, this one by agent 2, and so on. It seems simple. It is not so simple, the method, the protocol of privacy. I tried to simplify it for this presentation. And it means that you need all these 3 matrices, but no one knows all the 3 matrices. That's why you keep it private. So you do this for each one of the time series, and then we get an encrypted version. For the explanatory variables, we do the same process. So you still have the 3 matrix here, but we have another one that it was constructed by the own agent, in this case by agent 1. So he's the only one who knows it. And it is used to encrypt, to get the encrypted coefficients. So it's essential also to keep the coefficients private. So with these 2 matrices, we do this for each one of the data. And with these 2 matrices, then we can apply distributed computation, ADMM, as I showed before, but with encrypted data everywhere. So you get in the end encrypted coefficient. And since each owner know their own matrix, they can do the opposite product and they get the original coefficients in the end. So these original coefficients would be the one that you obtain if you were not concerned with any kind of data privacy or confidentiality. So this is how the method works in simple ways, simple terms. One question that you might have is how you can communicate and exchange data. As I told you, this is an iterative process. We consider 2 schemes for exchanging data: a centralized model where you have a central node or a central agent. It needs to be someone neutral, or a peer-to-peer scheme where everyone communicates with each other. So the process starts that each agent calculates their own encrypted coefficients using their own data and a conciliation matrix that starts with 0. So this is an iterative process. So the first step, it starts with 0, and then each one of these agents here make this calculation. So this is the same in both approaches. Where is different is when they transmit some information. In this case, they have to share their encrypted data, encrypted coefficient. Centralized model, they share with the central node. In the peer-to-peer model, they share between each other. So after sharing these data, they have to make the computation of the next. So conciliation matrix, this is the next iteration. So it is the centralized node who makes this on this communication scheme. On the peer-to-peer, it is each agent who makes this calculation. So, and then after making the calculation, they send the conciliation matrix back to in this case, the central node back to the peers. In the case of peer-to-peer, they share between peers. So with this approach, we can explore different schemes for information exchange, going from the centralized model with a central node to a peer-to-peer, a fully peer-to-peer scheme. This will be used depending on the kind of use case we are exploring. For example, centralized model, the central node can be a TSO or a DSO. Okay, so just to conclude my part of the presentation, so we have tested these in a data set in Évora, Portugal, with 44 domestic PVs, and we generated some results with these real data. So first we tried to see the impact of communication failures, or asynchronous communication. So since you have multiple agents and data owners, you never know if One of them might have a communication problem and you cannot wait for his data or for his transmission. So we make some kind of robustness test of this. So you can see with 50% failure for the central and peer-to-peer scheme, we see that the peer-to-peer is much more robust, but both are quite robust if you have half of the data owners having communication problems. Even with 90%, this is an extreme case. So you have the central and peer-to-peer. You see that the peer-to-peer, it's not very different if you don't have fails, but you see that the central scheme, that is the red line here, is very influenced by the failure of communications and get poor performance. So we can say that the best performance in terms of communication failure is from the peer-to-peer scheme. It's more robust because you have more redundancy on the communications, which doesn't happen with centralized scheme, and also anticipating a question from your side about the computational performance. Most of let's say the computational needs are related with the privacy protocol. So it takes more than 1 minute for 44 domestic PVs. Nevertheless, there is other alternatives for guaranteeing privacy that takes much more time and they are much more time consuming. So in terms of accuracy, so forecasting accuracy, you have here the root mean square error improvement of the proposed privacy vector autoregressive, and we compare with two state-of-the-art methods. One is the typical autoregressive. It means that you use data only from the same data owner. And another one is an analog search that includes data from neighbor sites, also includes privacy, so it can guarantee privacy. But this was a paper and a method published by EDF some years ago. They are not very concerned with accuracy. So you can see that our proposal have improvement on average more than 20%, 10% for the first hour, and can go up to 20%. And you see that we outperform all the methods for each lead time up to 6 hours ahead, and we guarantee privacy, which is also an important requirement. And an important conclusion is also to pass the word to Liang and to data markets, is that we saw that some data owners, their data contribute to improve the forecast of their competitors, but the data from the competitors didn't improve their forecast. So even if you guarantee privacy, those agents doesn't have any incentive to share their data because they don't take benefit from the data from the others. So this is where data monetization and data markets makes all the difference. And this is a good punchline to pass the word to Leah, that will talk to you about data markets.
Thank you, Ricardo. I'm going to share my screen. I think, let me know if you can't see my screen, but I think it's shared. Yes. Yeah, thanks, Ricardo, for the introduction of collaborative learning and data monetization. So I'm going to continue on talking about the monetization of data specifically in the context of data markets. Let's start with some basics. In a data market, the key players are the data buyers and the data sellers. And since we're talking about a market, we would like to put the value streams in monetary terms. And these monetary terms include the seller's cost of offering data, the buyer's profit, and also the payment from the buyer to the sellers. And in terms of the market procedure, I'm going to use a simple illustration to demonstrate that. So now you have a single buyer, B, who has information D, and then the buyer can make a profit F that as a function of the information they have. So F of D would be the profit that buyer B makes. And now you have a seller who has some additional information, delta D. Well, traditionally, without a platform to share your data, then this would be the end of the story. So the seller gets to keep their data and the buyer gets to make a profit out of the data that they already have. But with the existence of a data market, you have the opportunity for the seller to actually share the data with the buyer. And a few things can happen from here. The first one is that, first of all, the buyer can make an additional profit using the additional information. And this profit is represented by delta F. And now the total profit of the buyer becomes F of D plus delta D. And I'd like to note here that we're talking about data here in strictly volumetric terms, but in real applications, the data doesn't have to be volumetric. It can be, you can make a profit of better quality data or different types of data, but just for simplicity here, let's just focus on the volumetric data as a way to monetize data. And so now, because of the sharing, the seller also has to suffer a cost. And this cost could be from collecting the data or processing the data, or even just transmitting the data to the buyer. And more importantly, the seller also suffers a cost from the loss of privacy or competitiveness if you're in a competitive market. So in order to convince the seller that they should share the data, the buyer would have to share a part of their additional profit with the buyer to incentivize them to share the data. And obviously, this R value has to be smaller than delta F for the buyer to make a profit and for this whole trade to make sense for the buyer. But if the R value is too small, that it doesn't even cover the cost of the seller, then obviously the seller is going to say no. So it's a tricky question on whether how you can determine this R value so it falls between the value of the C and the value of delta F. And only when that happens, this trade can go ahead, and which would make sense for both the seller and the buyer. And again, the privacy value is included in the cost of the seller. So by having a compensation that's higher than the value of privacy that the seller sets on their own privacy, it means that the seller will be willingly sharing their data without additional concerns about their privacy. So when we're talking about privacy preservation in this talk, we're not really talking about the encryption or the processing mechanisms to actually make the data more private, but we're talking about the mechanism so that you can compensate the privacy losses for the seller. And now you end up with this payoff allocations where the seller gets R minus C and the buyer gets delta F minus R, and both of these terms are positive. So it's a win-win situation. And now if you generalize that framework to a more general, potentially multi-buyer, multi-seller framework, then you could have a monopolistic data seller model where you have a single seller but multiple buyers, or reversely a monopolistic data buyer model. Or if you have actually multiple of each, you can set this market up with a peer-to-peer architecture where every single seller can trade with all the other buyers, and every single buyer can also trade with all the other sellers. Alternatively, you can have a centralized model where you have a central market operator that aggregates the data of all the sellers and distributes them to the buyers and collects the payment from the buyers to redistribute to the sellers. And since we're talking about smart for us, how do we apply this data market framework to an energy market? For people who are familiar with the energy market, you will notice that actually this figure here looks very similar to an energy wholesale market. All you need to do is to replace the centralized data operator with the wholesale energy pool, the buyers with the the sellers with the generators and the buyers with the retailers. And to expand that to the energy retail market, then you just have the retailer able to redistribute the energy they purchase from the wholesale market to the end customers and make a profit out of it by marking up the price. So if we strip the market layers on this and think about how we can apply the data market on top of this energy market, coincidentally, or not coincidentally, as a matter of fact, you have already forecasting going on in the energy market. As Ricardo mentioned, the generators, especially renewable energy resources, they have to forecast their generation in order to bid into the wholesale market. And for the retailers, they also have to forecast their customer loads. so that they can also bid into the market to purchase energy. And these exercises are for the purpose of trying to meet the real-time demand with real-time supply. And because when there is a mismatch, the system operator has the obligation to activate certain balancing mechanisms to actually meet the demand with the supply. And that cost of the balancing mechanisms is called the imbalance cost. And that gets eventually passed down to both the generators and the retailers, which is why the retailers and the generators both have incentives to improve their forecast to reduce their imbalance costs. So now we think about maybe there is an opportunity here for them to improve their forecast by participating in data markets. So this is the end figure we're looking at. It's a very complicated figure, so I'm going to separate it into two parts to discuss. So if we look at the consumption side, when the retailer is bidding into the market, the wholesale market to purchase energy, the retailer can potentially get additional information from the customers to improve their load forecast, which is why we have the opportunity to set up a consumption side data pool to offer this mechanism. And as a matter of fact, nowadays, the retailer is already getting information from the customers through smart meters. But the difference here is that we are proposing a mechanism where the retailer has to compensate the customers for the data. And also we, at the same time, by compensating the customers for the data, the customers would have more incentive to actually offer more data to the retailer to improve their forecast. And at the same time, some customers may actually reject the offer just for purely privacy concerns. And we have summarized this work and submitted it to a conference, the IEEE Power Tech for next year. And this work is also has been uploaded to archive, so you can access that for free. And from the other side, on the generation side, the generators, like Ricardo mentioned, they have an obligation to forecast their energy supply in real time. And so they also have the incentive to trade data with each other to improve all of their forecasts. And I'm going to use a simple illustration to also demonstrate that. So if you have two wind farms, they both do their forecast and they bid into the wholesale market. And in real time, they deliver their energy. And this delivery is going to be different from their forecast because no forecast is 100% accurate. And that incurs an imbalance cost, which is why there's an opportunity for them to trade certain data, including numerical weather predictions or power measurements or historical data, for them to help each other improve their own forecasts. And eventually reduce their imbalance costs. So this is the market step number one from the market procedure that I talked about, where the buyer can benefit from additional data from the seller. And now the seller, in turn, has privacy or competitiveness issues because they're sharing their data with their competitor. So which is why the buyer has to offer a data payment to give them incentive to actually share the data. And this is the step number two, when the buyer offers a payment to the seller. And step number three is to say that, okay, the data payment has to be somewhere in between the loss of privacy cost and the imbalance cost savings for it to make sense for both the seller and the buyer. So now we completed all three steps. We reach a point where both the seller and the buyer can benefit from the market. And remember that when the forecast is more accurate, you also reduce the need for balancing mechanisms, meaning that you can reduce the cost for the whole system. So eventually the energy price is going to go down, which means that we actually achieve a higher total social welfare. So it's a win-win-win situation. Now expanding that to a more general framework, when you have multiple agents, again, you can have a peer-to-peer setup or a centralized data pool setup. And this work has been also written up and proposed by our colleagues, Carla, Pierre, and Ricardo, in their work towards data markets and renewable energy forecasting, which has been published or accepted to IEEE transactions on sustainable energy. And you can access that if you would like to. So going forward with the research, we realized there's a lot of challenges in establishing the data market. First of all, the cost of privacy is very highly individual. Everybody has their own price on their own privacy, which makes it very difficult to quantify, which means that also we would need to have a mechanism for people to reject, exchanging data in the market, which we do not currently have. And secondly, data is a very unique commodity. It's digital, and if we just compare that with simply energy, we can see that in terms of the production and replication, energy is produced at a very clear cost. No matter what the resource is, you know how much you would have to pay to generate 1 unit of energy. As opposed to data, where it's usually a side product and it's produced at almost no cost, and replicating it also means that it's no cost, and which this gives an opportunity for market manipulation where people can replicate their data sets and bid into the market multiple times and get multiple payments. So we will have to think about market mechanisms to prevent that and even penalize such market manipulation strategies. And secondly, in terms of value to the buyer, energy is additive. If you need 1 unit of energy to keep your light on and another unit of energy to keep your TV on, then you need 2 units of energy to keep both on at the same time. But in terms of data, the value of a data set is highly dependent on what kind of data the buyer already has. For example, for using forecasting as an example, if the buyer already has perfect information of the future, then whatever data set you're going to provide is going to be of 0 usage for the buyer. But if the buyer has no information about the future, whatever data set you're going to have that can get the buyer closer to the realization of whatever they're forecasting, then the data set has some value. And this combinatorial component makes it very difficult to price data. Not like energy, you can decide the price in advance. For the data to realize its value, you have to wait until real time and see whether the data set you got before actually got you closer to the realization. Which means that in the market framework, we have to think about the value of data in expectation, especially in a probabilistic forecasting context. And that makes the model even more complicated. So to conclude, Ricardo talked about in the first part of the presentation, talked about the collaborative learning, how that could improve forecast accuracy, which may likely yield additional individual or societal value in the market. And in the second part of the presentation, I demonstrated a few examples of data markets and showed how redistributing the added value to the participants, you can incentivize data exchange and also help to address some of the concerns about the loss of privacy and competitiveness. And in our ongoing research, Smart4S is planning on designing some suitable marketplaces for data trading and develop concepts and prototypes to increase awareness and also for people to toy with to understand the value of data markets. And going forward, we also would like to extend the concept to use cases outside the energy sector and collaborate with other domains and technologies, etc. And with that, that would conclude my presentation. And here are some references that we have mentioned in the presentation, and you can feel free to look them up if you're interested. And just as a reminder, this is the second installment of the Smart4S webinar series, and we have 4 more coming up next year. And if you want to be in touch, you can sign up using this link for our newsletter to be informed. And here's some additional information on how to contact us and also how to follow Smart4S and on the website or on the social media. And with that, thank you very much for listening, and we can open up the floor for questions.